Hi guys, so in this lecture we'll be continuing on seeing cyclic compounds. So our new topic is cyclic compound. Okay. So you know that the cyclic compounds, like we have cyclopropane, cyclobutane, cyclopentane, cyclohexane. Okay. So all the atoms in the rings are sp3 hybridized. So all should be ideally having 109-degree angle between them, but due to the ring structure they only enjoy 60-degree here, 90-degree here, 108-degree here, and 120-degree here. So what is the strain? The strain is just subtract the sp3 hybridized ideal angle from the actual angle they have in the ring and take the modulus. So strain here is 49-degree. Here let me write it with a different color. Strain here it would be 49-degree, here it would be 19-degree, here it would be 1-degree, and here it would be 11-degree. But out of all these rings, you should see that, or you should have thought that this should be the most stable ring out of all the 4 rings. But the counter case is this is the most stable, and I'll tell you the reason why this is most stable, because this actually exists as in a chair form. So this exists in chair form. So by chair form I mean that this actually exists somewhat like this. This is how the cyclohexane ring exists. Hence the relative stability order is order is 6 member ring, then 5, then 4, then 3. Okay, why? Because 6 exists in chair form. So let's see the chair conformers of cyclohexane. So chair conformers of cyclohexane. Okay, so if you see the structure of cyclohexane, it is something like this. So in this case you would have, suppose this bond is A, this is B, C, D, E, F, then A is parallel to D, B is parallel to E, and F is parallel to C. Okay, so let us talk about the axial and equatorial bonds in case of chair form of cyclohexane. So this is the ring we have. So in this we have 2 hydrogen atoms attached to each of the carbon atom. So these positions are wherein hydrogen attaches itself. These positions are called axial positions or axial bonds, is shown by vertical line with alternate up and down, is shown with alternate up and down positions. Okay, and if we have something like this, then this then all these positions are called equatorial positions. Okay, so equatorial positions are also alternatively up and down, as was the case with axial. So one hydrogen attached on this carbon atom would be axial and the other would be equatorial. Similarly for all the remaining 5 carbon atoms. Okay, so the complete structure of cyclohexane would look something like this. This is axial, this is axial, this is axial, axial, axial and axial, and the equatorial are, these are all the equatorial positions, up, down, and this is also up. Okay, so let us look at a compound in which H would be axial, and so in this compound, in every carbon atom of cyclohexane ring there would be 2 atoms, one would be D and the other would be deuterium. So H will actually, we made it to occupy the axial position and D to be the equatorial position. So we will have D here, D in this equatorial position, down equatorial position, up equatorial position, down equatorial position, and again up equatorial position. Okay, so actually how to identify cis trans isomers in di-substituted cyclohexane. Okay, so identification of cis trans isomer. So identification of cis trans isomers in case of cyclohexane. Okay, so we have first example, we have a ring in which we have CH3 at the down equatorial position, H as the upper axial position, H down here and CH3 up here. So this is trans. Why? Because H is up axial, CH3 is down equatorial, this CH3 is up equatorial, and this is down axial. So the higher priority groups, which were these, are at opposite ends to each other, so this is a trans. Okay, so now let's have a look at this example wherein we have cyclohexane and this is down equatorial, I'll come to that later, and this is also down axial. So if I write it down, this down equatorial and this position is down axial. So both the higher priority groups are in the same side or in the downside of the 2 carbon atoms, hence this is cis. Okay, so let us now construct a table out of the different axial and equatorial positions of substituents of cyclohexane, and then let us see which 2 positions are cis and which 2 are trans. Okay, so let me make a cyclohexane ring, a big cyclohexane ring. Okay, so in this ring I am just marking the substituents. A, E is the equatorial and A is the axial position. Okay, so in the table let me draw that which would be cis and which would be trans. So when we are doing the comparison between 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6, 2 comma 1, 2 comma 2, and so on. Okay, so what would be the answer for cis at, okay, let me mark the carbon atoms as well. So this is first, second, third, fourth, fifth, sixth. Okay, so between 1 and 2 the cis would be AE and EA, for and trans at 1 and 1 comma 2 would be EE, AA or EE. Okay, similarly for 1 and 3 the cis would be AA and EE, and trans would be obviously AE and EA. Similarly I can fill it for 1 comma 4, which is EA. For 1 comma 5 again the same. For 1 comma 6, for let's say directly jump off to 2 comma 3 here, and let us jump to 2 comma 3 here and 2 comma 4 maybe here. Okay, so what would be the positions for 2 comma 3? It would be AE EA and AA EE, and for this it would be AA EE and EE AA. Oh sorry, AE EA. Okay, so this is the positions of cis and trans for the axial and equatorial positions at the given carbon positions. Okay, so with this we end our this lecture, and we'll see some of the more examples related to the chair form of cyclohexane in the next lecture. So till then, good luck and good